For this next incline problem, we have a 1.2 kilogram mass, which is connected by a pulley to another 3.6 kilogram cart that's sitting on a frictionless incline. And the angle that's given to us is 26 degrees. And if the 3.6 kilogram is allowed to move freely, we want to find the acceleration for this particular system. Okay, just by taking a look at this diagram here, I noticed that the 3.6 kilogram object is heavier than the 1.2 kilogram object. So the system is actually moving in the direction of the heavier object. Okay, so that cart's going towards the right, and the 1.2 kilogram object is going in the upwards direction. Okay, after that, let's go ahead and create a free body diagram here. So we have a force of gravity acting downwards, and we also have a force tension on the rope. And the 3.6 kilograms, since it's attached to the same rope, we also have a force tension there. And then we also have a force normal like that. And we also have a force of gravity like that. So this right here is your free body diagram. And what we're going to do next is we're going to try to create a F-net equation for this entire system. But in order to do that, we also have to consider some other components to this for this type of incline problem. Now, your force of gravity right here, it actually creates another, this is not part of the free body diagram, but it creates another kind of force in parallel to the incline. And I'll label this F, and I'll call all that X, F of X. So there's another force that's parallel there, but that's not part of your free body diagram. However, the Fx component there, that will actually help us create a F-net equation for the system here, which will be very useful. So if I create a F-net equation for this entire system, okay, we know the system is moving towards the right. So if I create my equation here, and if I start combining all the forces here, I have my Fx force, and then I'm going to minus the tension. So that is the F-net equation for the 3.6 kilogram cart. And then I'm going to add that to the next situation over here. And since the system is going upwards here, I'm going to start off with the tension, and then I'll subtract the force of gravity. All right, so this is the F-net equation for the entire system here. And you'll notice that this tension, which is negative, and this positive tension, that will cancel out. So now you're left with the force in the x direction, and then you subtract that from the force of gravity. And this is equal to your F-net for your entire system. Okay, so let's go ahead and see if we can just break this down now. So F-net using a Newton's second law is your mass total times your acceleration. And this Fx component, this is actually broken down in class, but it's actually your mass times the acceleration due to gravity times sine of the angle. And then we subtract Fg, which is just mass times the acceleration due to gravity. And I just want to emphasize that these two masses, they're different. Okay, so the mass in the red font represents the cart on the incline, and the mass over here in the blue font, that's actually the mass of the 1.2 kilogram object that's being lifted up. Okay, let's go back to our diagram here. Let me kind of just erase all the forces now. And if I look at the total mass now, it's 1.2 plus the 3.6. Okay, so this is going to be 1.2 plus the 3.6. And I'm going to multiply that by my acceleration, and that will equal to mg sine theta. Now this mass is the mass of the cart, which is 3.6, times the acceleration due to gravity, which is 9.80. And I multiply that by sine of the angle, which is sine 26 degrees. And then finally, I subtract that from mass times the acceleration due to gravity, and this is the 1.2 mass here. So this is the 1.2 mass object. And then I multiply that by 9.80. Okay, so then from here on, it's just we're just creating some calculations here now. So if I just add the 1.2 and the 3.6, that's going to be 4.8 times the acceleration equals 2. And then if I multiply all of this out in the red font, I will get 15.466. And then if I multiply all this in the green font, I get 11.76. Okay, and then we just kind of solve for a now. So 4.8 times this acceleration equals 2. So 15.466 minus 11.76 is going to be 3.706. Now our acceleration now is going to be the 3.706, and then we're going to divide that by 4.8, and that gives us 0.772 meters per second squared. And that is our acceleration for this entire system. For our next incline question, it's very similar to the previous question, except that we do have to consider friction now because we have the coefficient of friction as being 0.22 for this incline. Okay, so just like the previous problem, we need to calculate the acceleration of the system, and this has to happen when the masses are being released, right? Okay, so if the masses are being released, we always look at the heavier object, which is the 10 kilogram object. So the system is actually going in the downwards direction, and the 6 kilogram object on the incline is going up the incline. Okay, so that's what happens when the masses are released. Now let's go ahead and create a free body diagram. So we have F of G right here, FG there, and then we have the tension right there. And for the 6 kilogram object, we have the tension as well, because it's sharing the same rope. And then we have our force normal, and we have our force of gravity, and we also have the force. Actually, let me just kind of draw the force of friction over here. So this is the force of friction like that. Okay, so there is our free body diagram right there. And once we have a free body diagram, we have to now create a F net equation for the entire system. Okay, so before we create the F net equation for the entire system, let me just erase the force normal and the force of gravity here, because if this incline is going up, it's important to note that there is another force here that's parallel to the incline, which is your force in the x direction there, and that's always going down the incline, regardless if the 6 kilogram object is going up the incline or down the incline. The force in the x direction, which is parallel to the incline, is always acting in the downwards direction here. Okay, so these are the forces that we're going to be using to create our F net equation here. So let me go ahead and let me just kind of write this, shrink that down, and let's go ahead and write a F net equation just below this. So F net. Okay, and we've already established that this system is going down and the object is going up the incline. So if I take a look at this particular part of the problem, we create our F net equation by saying Fg minus the tension, and then we're going to add the forces in this direction here. So since that's going up the incline, we'll start off with the tension, and then we're going to subtract the force in the x direction, and we're also going to subtract the force of friction. Close that off. Alright, so there is our F net equation for this particular system here. And we notice that the tension here, which is negative, and the tension in the rope over there is positive, those will essentially just cancel out. And now you're just left with the force of gravity minus the force in the x direction, and then minus your force of friction. And that's going to equal to your F net. Okay, let's go ahead and now use Newton's second law here, which is the mass total times your acceleration equals to Fg is the same thing as mass times the acceleration due to gravity, minus, now the force in the x direction is always going to be the mass times the force of gravity, 9.80, times sine of the angle. And for your force of friction for these incline problems, it's always the coefficient of friction, which is mu, times Fn, the force normal, times cos of the angle. Okay, now we know Fn is the same thing as mg, right? So or Fg, and Fg is the same thing as mg. So if I just erase the Fn, I can just write this as mu times mg times cos of the angle. Okay, And we want to emphasize that all these masses, you got to be very careful with all those masses because you have to pick the right object, right? So let's go ahead and start on the left-hand side here, which is the mass total. So if I go back to my diagram here, we have 6 kilograms and 10 kilograms. So let's just go ahead and add that together. That's going to be 6 plus 10 times the acceleration. And now I have mass times the acceleration due to gravity here. This is the heavier object, which is 10 times 9.80. Okay, and then the mass over here is the mass on the incline, right? So this is going to be 6 times 9.80 times sine of the angle, so sine of 36 degrees. And then minus the coefficient of friction, which is going to be 0.22, times the mass of the object on the incline, which is 6 kilograms, times 9.80 times cos of the angle, so cos of 36 degrees. Okay, so a lot going on in this particular equation here. So let's go ahead and start calculating the numbers here. So 6 plus 10 is going to be 16, so 16a equals 2. And then if I multiply this, 10 times 9.80 is going to be 98. And then minus, 6 times 9.80 times sine of 36 degrees is going to be 34.562. And then finally, if I subtract the force of friction here, that's going to be a 10.465. Okay, if we keep on going here, we have 16a equals to 52.973. And then we can divide both sides of the equation by 16, divide that by 16, and your acceleration for this particular problem is going to be 3.311 meters per second squared. For this next incline problem, the question is asking what force F applied parallel to this incline would make the 15 kilogram block shown below move up at constant speed up the incline. Okay, great. So there's a lot going on in this particular problem here. So let's go ahead and draw a free body diagram if we can. So, okay, here's our force normal. Here's our force due to gravity right there. And we're trying to push this incline, this object up the incline, so that's moving at constant speed. So, this force right here, let's just kind of put the force up there. And since the object is going up the incline, we do have a force of friction. So that right there would be your free body diagram. Now, once you've established a free body diagram, you want to create a F net equation for the entire system. And one other force that you have to consider is the force that's moving in the x direction. And regardless if the block is going up or down the incline, there's another force here that's parallel to the incline, which we'll call force in the x direction there. Now, the force in the x direction, that's not part of the free body diagram, but will help you set up the F net equation here. So if I erase this and this, now we're in a pretty good situation to set up an F net equation here, because all the forces now are kind of going the same direction now. So if we try to create a F net equation for this entire system, we know the system is going up the incline. So we'll start out with the force in the blue font, and then we're going to subtract the force in the x direction, which is parallel to the incline, minus the force of friction. Okay. And then if we go ahead and use Newton's second law here, this is going to be the mass total times the acceleration equals to the force in the blue font minus the force in the x direction, which is mg sine theta, minus the force of friction, which is basically mu Fn times cos of the angle. And we know that the F force normal is the same thing as the force of gravity, and we know the force of gravity is equal to mass times the acceleration. The acceleration due to gravity there. Okay. Now, one more thing that we have to consider here is we're trying to go up the incline at constant speed. Okay, so constant speed means you're not accelerating, all right? So that means you're not going up really fast and faster up the incline. You're moving at a constant speed, so your acceleration there is just going to be 0. So your total mass times 0 is simply just going to be 0 on the left-hand side. Okay. So if I have to do this actually correctly, it's actually going to be the mass of the object, which is 15. So 15 times 0, which equals to the blue font, the force, minus mass times acceleration due to gravity times sine of the angle. So this is going to be 15 times 9.80 times sine of the angle, so that's going to be sine of 26, minus the coefficient of friction, which is 0.23, times the mass, which is 15, times 9.80, times cos of 26 degrees. Okay, so a lot of calculations again for this particular problem. Over here again, 15 times 0, that's going to be 0, equals to the force that you need, minus, well, 15 times 9.80 times sine of 26 degrees is going to be roughly 64.441. And then we're also going to subtract the friction here. So if I put that into a calculator, we get 30.388. And all we're doing now is we're taking these numbers here, we bring that to the left-hand side, and it turns out that the force that we need is about 94.829 newtons. All right, so that's the force that needs to be applied. So if I go back to my diagram here, let me just erase all this. So this force right here has to be about 94.829 newtons so that this block moves up the incline at constant speed. Okay, so that concludes this homework video guide.